Well, hello and welcome to the first ever 3D in 30. This is Velo3D's LinkedIn live channel. We are really excited to kick this one off. It has taken us a little while to get approved, but we finally have it. And so now we want to put out some live content for you. This is a bit of an evolution for us. We've been doing the webinars, and what we found in the webinars is that you guys have a lot of questions. So we wanted to create a channel that is just that, allows live interaction. So please feel free to leave us a comment, a question, smiley face if you want to. Just let us know how we're doing. We would love to field some of your questions today, so please bring them in. We plan to do this about every 2 weeks. And so we're going to get started today. I'm excited to kick off our first session. We're titling this one, What is Laser Powder Bed Fusion? We're going to start right at the very beginning. Joining me today is Dr. Zach Murphy, our VP of Technical Partnerships, and also Velo3D's Chief Marketing Officer, Renette Youssef, sorry. So welcome to the show. Renette, I'll let you do a little bit of introduction. Tell us a little bit about yourself.
So I think I was muted. Okay. So just to start, I am Renette Youssef. Excellent. I'm the CMO here at Velo3D. I started 6 months ago, and that was really my first exposure to 3D metal printing and laser powder bed fusion. I met Benny, and he sold me on the fact about joining the team because this technology is actually really changing the world, and I fell in love with it. So I'm really excited about this this session today and really diving deep with Zach.
All right, Zach, a little bit about yourself, please.
Yeah, absolutely. And I want to mention, I think it's only appropriate that we started the session with somebody muted in the world we live in these days. But I'm Zach Murphy. I'm a VP of Technical Partnerships here at Velo3D. My background is aerospace engineering. I did my doctoral work in hypersonic aerodynamics, which seemed completely unrelated for a long time, but now is becoming much more relevant in metal additive. I was then a customer first and foremost. So I worked at an oil and gas company where I was in charge of bringing metal additive into the business. And so that's really where I kind of got started with metal additive. Joined Velo3D a little over 5 years ago as the head of product and applications, and I've kind of migrated through different roles in the company and got to interact with all of our customers on a number of different levels. So excited to be here and do some more missionary work.
Now, you mentioned you started with hypersonics, then you went to oil and gas. How are those related?
Not very much. So my first job out of grad school was with a renewable energy company that then kind of transitioned into something more lucrative in terms of making products for oil and gas. And so that's how I ended up in the energy business. So research engineering was really what I wanted to focus on, and oil and gas had some very well-funded research projects. So it was a fun time.
And it sounded like you've been in additive for a little while.
Yeah, so that was probably 9 years ago at this point. So not as long as some, but definitely have seen the industry and the technology evolve quite a bit.
And so Renette, kind of back to you. What was your first experience with metal additive manufacturing?
6 months ago, honestly, when I met Benny, when he was trying to convince me to join the team. My background is technology, mostly SaaS, and I had no exposure to manufacturing, 3D metal printing. And I really wasn't interested in taking the call. And the recruiter was like, please just meet Benny. And like I mentioned, like I was just so fascinated. So that has been my exposure, and obviously learning over the last 6 months and meeting people like Zach who completely sold me on the technology. So love it so far, and just this learning is so fascinating. And hopefully some of the viewers today get to see and hear why I'm so in love with it.
Yeah, and I think what we want to do is sort of copy the viewers. Some of our viewers might be new to the technology as well. I understand you have a couple questions that you want to get in front of Zach, so it seems like a good place to start.
Excellent. So Zach, you were the second person I met when I was introduced to Velo3D. And you sold me on it. But one of the things I really enjoyed when I met you was your ability to break down these complex concepts. So the first question I have is really starting from the basics, and it is, what is laser powder bed fusion, and why is it so important for us today?
Yeah. So laser powder bed fusion is one of the many, I guess, modalities, people call them, of additive manufacturing. And additive manufacturing and 3D printing are kind of analogous depending on who you talk to. But laser powder bed fusion is the process of making metal parts by melting a very fine powder with a laser. So it's a welding process fundamentally. And what we do is lay down very thin layers of powder, generally around 50 microns or 2/1000ths of an inch, kind of the thickness of a human hair, and then weld those with high-powered lasers to whatever's below them. And by doing this over and over and over, you end up making a three-dimensional part that's then directly usable in some pretty amazing applications.
So I'm guessing from your technology, from your explanation, sorry, this technology hasn't been, it's not new. Like, it's been around for a while. Like, when was it invented and who invented it?
Yeah, it's an interesting question, right? Because if you compare it to casting, then yeah, it's absolutely a brand new technology. But it really has been around since essentially the early 90s.
Okay.
It was some of the foundational patents came out of Germany.
Okay.
And I think Fraunhofer was one of the first places that it was really kind of put into practice. So it's been evolving over the past 25, 30 years into what it is today. And I think you're starting to see now it's becoming a real solution for production components and for these demanding applications. But yeah, originally out of Germany in the 90s.
Excellent. So if people weren't using additive or 3D metal printing, what would they be using instead?
So there are other ways to make metal components, and there's a lot of them, really. So whether it's casting, kind of a near net shaped component, and then machining, whether that's milling or turning that part to get the final geometry. There's also different ways of kind of putting parts together, whether it's brazing or welding, or otherwise building the part up from smaller individual components. But additive really is a great way to make a fully integrated part that is essentially what you would need for the end use application more directly.
So just to be clear, at the end of this, you do get a 3D metal printed part.
It's real metal, yeah. You get a part that is fully dense, functional component. If you're printing in titanium, it is a aerospace grade titanium component that then can be used in the appropriate applications.
Excellent. So I think we have a question, Mike. Is that correct?
Yeah, you mentioned 3D printing and additive manufacturing. What would be the difference? Why would somebody use one term versus another, or are they basically synonyms?
In my mind, they're more or less synonyms, depending on who's using it. I think there's a notion that 3D printing is used more in the consumer space. So if you're talking about, polymeric desktop printers or the 3D printer that you have in your garage that is like an FDM type of, fused deposition modeling, the glue gun extrusion type of printer, that's generally referred to as a 3D printing machine, whereas additive manufacturing sounds much more industrial and I think is used more in that context, especially by people who, like us, really want to talk to those industrial audiences.
And just a reminder, if you do have questions or comments, we are live, so feel free. I do see a couple comments here. Jen, that was a call out. Thanks, Mark, for that. It looks like our audio is up and running for everyone. So Eric, thanks for letting us know that the audio is running.
So Zach, you also mentioned you've been in additive for around 6 years. So I'm sure in that time you've heard some misconceptions. What's the most common misconceptions around laser powder bed fusion?
One is what we just mentioned, right? Is that the part that you get at the end of the day is not fully dense real metal. I think, it's hard for a lot of people to really envision that the thing that you pull out of this laser printer system is a part that you can then stick in a jet engine or a rocket engine. And to be sure, there are post-processing steps for heat treatment and other things to get it to the final mechanical properties, but it really is end-use functional component, and that's I think one of the biggest evolutions in the technology, even just the laser powder bed technology over the last 20 years. I think one of the other misconceptions is that it's kind of an unapproachable technology, right?
Yep.
It seems difficult and sophisticated, and I think one of the things that we've focused on at Velo is building a lot of that sophistication into our machine and our software, so that for the end user, it's much simpler to be able to kind of pull in a part and print it and have something come out of the machine at the end of the day that is useful.
So you also mentioned jet engines. What other applications can you do besides jet engines?
People have been doing all kinds of different applications over the history, I think, of laser powder bed fusion. I think some of the earliest applications were around tooling. And when I say tooling, I mean like injection molding tooling, where you have metal components that you are pressing together and then injecting plastic to make water bottles or anything really. And it was useful there because you could print parts that had internal cavities that you could pass cooling fluid through. So these are conformally cooled tooling inserts. And from there, it's evolved. A lot of people are using it in medical orthopedics and other applications. We tend to focus on we like to say things that fluids flow through or that transfer heat. So that's really aerospace propulsion type of components, heat exchangers, pumps, valves. Those are really where we tend to have quite a bit of value.
Excellent. So, and we don't just do it for prototyping. It can be used throughout the whole manufacturing process. Is that correct?
Oh yeah, absolutely. Our goal is really to drive the technology further and further into production. And I think that is also an evolution of the industry, right? Initially, it was very much used for prototyping and kind of form, fit, function testing before you would then take that part and make it some other way. And we really want to make it clear that with the technology as it is now and with the technology as we've implemented it, you can use it for prototyping and to kind of rapidly iterate and get the product to the place where you want it in terms of performance and everything else. But then you can also use that same manufacturing technology in production in a cost-effective and consistent way.
So what are the other advantages? You mentioned cost effectiveness. Like what other advantages does laser powder bed fusion or 3D metal printing provide?
So 3D metal printing as a whole has several promised advantages, I'll say, that have always been kind of the thing that people have been focused on when using it. So anything that has kind of an organic shape or internal channels that would be hard to manufacture with a different process is really well suited for metal additive. Also, lightweighting, right? People use it in aerospace because you can take a lot of the weight out and increase the functionality of components at the same time. Part consolidation is another big one. I think, we have some examples with like the Sierra Turbine's combustor core for a micro turbine that reduce the part count by, almost an order of magnitude.
Amazing.
So you can build a lot of functionality in and then print it in one go.
So we do have a couple questions coming in, a couple on quality. And so one of the questions is, what are the quality control processes that would be available for 3D printed parts? How do they analyze the parts? And maybe those are two different questions.
Yeah, there's kind of the conventional quality metrics that people use when manufacturing metal components. So a lot of non-destructive testing at the end of the day for parts that you're making. That can be as complicated as full CT scans of components, or you can do things like the fluorescent dye penetrant testing to see the surface quality. A lot of that NDT is very similar to what you would do with a machine component or a cast component. But one of the things about metal additive and about the system that we're bringing to market is that there's quality and metrology in the process itself. So you can know to a really high level of detail what is occurring as you're actually making the parts. And the whole goal there is to give end users confidence in the quality of the printed part. So people talk about confidence intervals as kind of a statistical measurement of quality. And Velo's Assure quality control software is really around giving the end user a confidence interval, kind of a bounded interval, so that they know that the part is good. And Mike, I think, as you like to say, engineers don't use parts they can't trust, and we stand by that. That's something that we definitely have to address.
Yeah, that was an interesting
Some other
conversation. Oh, sorry. I was just going to give a little bit of background on that. Greg Brown, our VP of Process Engineering, he's the one who actually came up with that. And my first thought was, hey, you're going to have these parts and they're going to go bad. He's like, no, engineers don't let it get to that point. And it really does come up earlier in the process. Like you don't include optimization features if you can't qualify it, or if you can't manufacture it. But if you can't manufacture it in a verifiable process. So it was interesting to see the coupling and the connection between performance improvements and it coming down to quality control.
Making cool geometries is just that, right? Unless you can kind of validate the quality of the part, you've made a really cool desk ornament.
Or a trade show. Or a trade show part.
Yeah.
Yeah, no, that's definitely been out there. Renette, you said you had a couple more from the audience?
Yeah, and I think there's some really good questions that maybe we can keep taking.
Let's see here. Okay, this is about shortages in the global supply chain. So what are some of the ways that 3D printing can play a role in filling in the global supply chain?
Yeah, that's a very timely question too, right? I think one of the things that we've seen is that a lot of the traditional supply chains that rely on kind of distributed manufacturing, like casting as an example, have seen some pretty intense disruptions over the past year. And one of the nice things about metal additive, and one of the things that we've seen through some of our collaborations around distributed on-demand manufacturing, is that it can decrease the reliance on these more complex, more, I guess, conventional supply chains, in a way that when you need a part, you can print it essentially on demand, and have it without necessarily needing to ship something across the Pacific Ocean. And especially in industries like oil and gas, I think that's something where you see a lot of demand and people starting to take it much more seriously, right? If you can have printers at your field locations so that when something goes down, you can print the part instead of having, millions and millions of dollars in a warehouse and inventory, then that becomes a really attractive proposition pretty quickly.
And is it, obviously you could print the part, but is that all there is to it? What is the role of post-processing in this, and how does that vary?
I think there's even a question before that, right? Which is, can you print the part?
Yeah.
So a lot of times you've run into components, we deal with this with shrouded impellers or pump components or other kind of industrial geometries. They don't lend themselves well to traditional metal additive manufacturing. And that's where Velo's technology has really excelled and kind of driven adoption, is that we're able to print a much larger envelope of geometries, which means that then you can start to realize that distributed manufacturing in a much more scaled way. And I think when you talk about post-processing, one of the things to recognize is that metal AM is a tool in a manufacturer's tool belt, and it rarely is the only tool needed to get to kind of the final component. So like I mentioned previously, whether it's heat treatment or final machining of mating surfaces, interfaces, seals, that type of thing, there's often some amount of post-processing, surface finish, machining, heat treatment that is required before you can stick the part in an oil well or a jet engine.
Oh, there's the most famous question that we get asked. It finally came in. How is it possible that Velo3D requires almost no supports? So what is it that we do to print SupportFree?
Yeah, it's my favorite question, I think, too,
I know,
at this point.
and it came in 21 minutes after the hour, so just putting that out there. So we're on record.
Yeah. I always like to say the answer is probably less sexy than people want it to be. We're a process company at our foundation, right? So what we've done is develop a process and then build software and hardware around that process in order to allow you to print without supports. So when it comes down to what enables us to do this, it really is around process control, around knowing exactly where you're operating in terms of a viable process window, and having the hardware to implement that correctly. So if you define the process that we've made in our print preparation software and flow very accurately and very well prescribed given certain geometries, you then have to be able to execute that as well. And that's where the Sapphire printer really comes in, both in terms of controlling the laser, right? In terms of the scan head system that we've developed from scratch, as well as the recoder system that gives you increased flexibility in terms of the protrusions that you can tolerate without essentially crashing your build. All of these things combine to make the process work. And that's how we can eliminate the vast majority of supports, especially as these overhanging surfaces get lower and lower.
I guess we probably should ask the first question is, why do you need supports at all?
Yes.
We'll go
or what are supports, right?
Yeah, what are they? What does that mean?
So as we were talking about at the beginning, this is a welding process and at its core. And what you see whenever you're welding something, like if you were to take a flat piece of metal and run a weld bead down the middle of it, the part would deform. And it does that because of some of the residual stress that's imparted to it as the melt pool, the molten metal solidifies. And in laser powder bed, the way that this kind of manifests itself is that the part wants to stick up out of the powder bed. So as you weld it, things start to protrude. And when we say supports, we're kind of doing everyone who's new to metal additive a disservice, because they're not supports. They're not intended to fight gravity. They're intended to hold the part down. Right? They're anchors. So, you don't need gravity-free printing to eliminate supports. You need to eliminate these anchors and keep the part where it should be. And if you don't have kind of the process and the recoder architecture that we have at Velo, you address that by applying supports. And I think you saw that in one of the previous screens. You can fill these parts with supports that are printed out of the same material. So this part, as an example, is a Hastelloy X alloy, and that means that all those supports are also Hastelloy X, which is not necessarily an easy thing to deal with, especially on these internal geometries.
Yeah, you can turn your printer into $1 million staple gun really easily. And I've heard sometimes the mass for the supports can be more than the mass for the part when you're done.
Yeah.
Conventional printers, yeah.
Yeah, there are all kinds of good reasons to try to eliminate supports where you can.
Zach, what's next with laser powder bed fusion?
The industry for a while has been driving towards higher productivity and larger parts. I think the process started on a relatively small scale with low power lasers, and one of the things that you see now is that to expand the markets that are addressable with laser powder bed fusion specifically, you need to expand the envelope of parts. So bigger parts, more lasers. So we have a product that we're starting to deliver in the fourth quarter of this year that's called the Sapphire XC. It's about 4 times the build area of our current system. It's about 5x the throughput. So in terms of cost effectiveness of the final printed part, it's really a step change in what you can do, what you can address with laser powder bed.
And that's 75% reduction, like that, more than half. Like that's not 75% is what it now costs, right? I'm reading that right.
If I understand your question correctly, yes.
So if it costs 4 of something today, it'll cost 1 of something.
Yeah, we've seen examples where it's it's a fifth of the cost. So you can really start to leverage that scale in production, and make some inroads into areas where right now it may not necessarily be as appropriate.
Okay, so we do have a couple more questions. So kind of coming back to our followers here. In which applications or production volumes do you identify AM is the key technology or the chosen technology versus traditional?
So you'll probably hold this against me for saying it, Mike, but I went to school to be a rocket scientist, and I guess kind of failed in that regard because I didn't ever end up working for a rocket company. But one of the things that we see is that rocket engines and turbo machinery associated components are one of the fastest adopters of the technology. But I think from an industry perspective, it's important to expand in more maybe well-established industries as well. So whether that's aerospace, or really we're seeing a ton of adoption in kind of the industrial applications. Like I said, pumps and valves and other kind of fluidic devices for those. Yeah,
I know just from some of our case studies, it's been hard to really pull out and say this is a heat exchanger or this is a combined. Like people just put so much together now. Maybe talk about that a little bit. You mentioned part consolidation and just feature consolidation. What are you seeing in the market? Are people really taking advantage of that?
Yeah, absolutely. And you see it in some of these kind of newer applications. I think microturbines are a really good example of this because, for a long time, there have been stories about like, we made a fuel nozzle and then had it certified and kind of going into production with that. But the cool thing about some of these smaller gas turbines is that like the fuel nozzle is just one part of it. You can print the fuel nozzle, kind of the entire combustor core with recuperators, with all kinds of different functional components in one part. And you can do it in some pretty interesting ways, some geometries that you wouldn't consider doing if you didn't have laser powder bed fusion.
Yeah, well, heat exchange was the one I was thinking. Like you could just put in heat exchange into any, I don't know, what I was thinking holder, but that's not the right word. Any assembly, if you wanted to. Yeah,
wherever you need to dissipate heat, you now can integrate, oil, air, fuel oil, any type of heat exchanger you might need. Put it right inside the component. Save space, save weight.
So Zach, have you got any advice for any of our viewers who are thinking about turning to like metal additive manufacturing or laser powder bed fusion for the first time?
I do. Yeah, I do have some advice. So, I mean, we love to see challenging engineering problems, right? That's where I think we really excel as a company, is helping people to look at their kind of disruptive systems and designs and figure out how to leverage the technology to make it better and to make it faster and easier. So I would say absolutely reach out to us through our website. We have kind of a way to contact our engineering team, and we're happy to discuss parts, designs, ideas, try to figure out a good way to leverage the tech.
Excellent. Mike, do we have one last question that we want to take from our viewers?
Yeah. So this one is one I actually got asked the other night over chicken wings. Is it possible to print multiple materials with laser powder bed fusion?
There are some people that are working on it. I think there's a lot of complications in doing it, because essentially what you're doing is, laying down a layer of a certain alloy, a certain type of powder, and filling up this build volume with that powder. So if you're starting to lay multiple powders down, it can make a lot of that, you can kind of foul the powder bed and make it not as usable in kind of subsequent cycles, which is one of the big advantages of laser powder bed. So it is becoming more of a reality, but right now laser powder bed is really mostly in real applications, limited to single material printing.
Okay. Well, let's take one last one then, and then we'll close out. We're kind of past our 3Din30 title here. Could you please comment on whether or not the support-free or supportless technology works for only Velo3D materials?
So I can tell you that it definitely works for the materials that we validated. We've been very deliberate in the materials that we've worked on because we always are really responsive to customer input and demands. So there are some materials that we haven't tried that I'm sure it does work on, but it's more of a bandwidth and demand question than a technical risk and feasibility question.
And if somebody is interested in printing in a material that we haven't printed in, what would be what could they do?
I would say the same thing. If you're interested in a certain part or component, reach out to us. Let's have a conversation about it. Right now, we're in the process of developing our new copper alloy. And that's basically coming straight from customer request with some pretty compelling applications behind it.
Awesome. Well, since you said copper, we're up on time. Thank you for joining us today. Be sure to follow us on LinkedIn so you can get more updates on LinkedIn Live or Velo Virtual, case studies, any content. As a reminder, our next session will be 2 weeks from now, and we're going to be talking about the switch to additive. So we're going to be diving in to the things you should know when moving from, like Zach mentioned earlier, casting or machining, welding, brazing, and now, or even conventional 3D printing if you want to now move to Velo's support-free solution. So, what should you know? That'll be in about 2 weeks. If you have any more questions in the meantime, reach out to info@velo3d.com or contact us through our webpage and speak to an expert. So we have our engineers are pretty much ready to help you.
Thanks so much, Mike. Thanks, Zach.
Absolutely. Thank you.